We're here talking about some work that we did along with some other people on measuring brain wallets. So who am I? If we can go to the next slide. I'm a newly minted professor of computer science at the University of New Mexico. Just finished up my PhD, and a lot of this work was part of my dissertation. I discovered Bitcoin back in 2011, and it's interested me ever since. I wrote my first Bitcoin papers in 2013, published in 2014. I'm also a con noob. This is my first hacker con.
I'm Ryan Castellucci. I don't do Bitcoin stuff professionally. This is just one of my weird hobbies. I think somebody described this as, oh, Ryan tries to prevent people from losing lots of Bitcoin, and generally this pisses them off. For my actual job, I do bot detection research for white ops, and then Bitcoin I have been messing around with since early 2011, and I'm not sure how many HackerCons I've been to at this point.
But it's not your first. So if we think about how to securely do key generation, we could look at a scheme like RSA. Now, a bunch of really smart people have taken a lot of years to write libraries in order to generate really, really big random numbers with very special properties. These numbers have to go through a number of checks and then make some calculations based on derived values. Now, Bitcoin uses an elliptic curve key generation. If you went to Ryan's talk, you know that what you have to do is generate a random number. Basically, what it has to be is it has to be 256 bits, and it can't be 0, and it can't be another number. So this key generation process can be fairly trivial. Now, there are ways of securely doing it. However, if maybe you don't trust your computer, you don't trust the hardware, you don't trust the random number algorithm that some person you've never met wrote, you could say, hey, why don't I create my own system? And why don't we base it around something really, really secure? I know, how about passwords? And so what these people did is they use this really easy to use tool. You just insert a password, and the Bitcoin private key is the hash of the password. Now, people have actually stored quite a bit of money with these schemes. And so on the flip side, so on one hand, there's these users that have lots of insecure money stored. And so naturally, there's this attacker ecosystem that evolves out of that. It's like a money piñata. You just have to guess the right password.
All right. I'm sure everybody has seen this comic before, but this is XKCD on passwords, and the passphrases that this suggests using are more secure than typical passwords, but they are not secure against offline attacks. So one of the offline attacks that I ran when trying to look at what passwords people had used for brain wallets was based on XKCD password generation. I found a couple XKCD password generator tools, used their word lists, and generated a lot of passwords. I think it was a couple trillion. So correct horse battery staple was actually a default password on brainwallet.org, which resulted in it getting used mistakenly a lot, and it was also involved in some of the Bitcoin spam attacks that happened. One of the ones that I found that was more obscure was expect pants size clue, which actually looks like it was a randomly generated one that somebody genuinely thought might be secure. That one held 2.18 Bitcoin in it. Then there was earth, air, fire, water, which is not random, of course. And then deal, iron, science, food. That one actually does seem random too, although it's only had a few cents in it. And due to the transaction that created it, it looked like it had been made by somebody who was just trying to put out bait to see who would take them. We also identified a large group of brain wallets that were created in August of 2014. All of them were extremely simple single-word passwords. There were about 15,000 and something of them, all created within the span of a few hours, and all of them had only tiny fractions of a penny worth of Bitcoin in them. So we've excluded those from analysis because they're not interesting. As far as other things tried, as I mentioned, XKCD style up to 4 words. For 4 words, I had to trim down the word list size just a little bit. So I picked words that were common between the 3 tools that I found. But for 3 words, I combined all of the lists and used all of the words, and got some hits there as well. Cryptocurrency IRC chat logs were sourced from my computer. I've been sitting on a bunch of cryptocurrency channels on Freenode for a good 6 years, and I just fed them all in as passphrases. That got some weird hits. Like somebody had used, there's a Bitcoin over-the-counter trading channel, and there's a bot you can authenticate against. And somebody used an authentication string that was posted in the channel to authenticate to the bot as a brain wallet password. Again, that was probably somebody just doing that to see how long it would take. Then there's a data set of Reddit comments that is available online. It's got comments for basically every subreddit since the beginning of Reddit, except for a few. Some comments have been deleted in there, but mostly it's complete. That was processed mostly to strip the markdown punctuation that Reddit allows and do some other minor cleanup. Wiki quote I scraped and turned that into a phrase list. Wikipedia. The Wikipedia list I used, as far as I can tell, was included with OCL hashcat at some point. That was the list that I found, the how much wood could a woodchuck chuck if a woodchuck could chuck wood brain wallet that had 250 Bitcoins in it, and I tracked the guy down, and he moved the Bitcoin out of that wallet and was very appreciative. Braining quote is another site I scraped. Basic normalization. Facebook names came from Skull Securities lists. Urban Dictionary I scraped. And then I purchased a song lyrics database that was fairly recent, and that was where I got that data. Outside of phrases, I think these lists should be familiar to a lot of people. The Rock U list is, of course, obligatory. CrackStation has a good list. There's one put out by a guy who goes by Nexito. I don't know if I'm pronouncing his handle correctly, but it is very large. I think it's about 40 gigabytes uncompressed and full of kind of garbage. So I cleaned that up down and got it down to about 4 gigs. But originally it had, for example, every 5-character ASCII string in there using printable characters. And having that in a list is not super helpful. Unique Pass is a commercial list that you can get fairly cheaply. I have a couple different versions of it because they update it, I think, quarterly. And Skull Security, as I mentioned, I used that. All of their lists, and I did a bunch of brute forcing. Every ASCII, printable ASCII up to 6 characters, lowercase letters up to, I believe, 8, numbers up to 10 or 11. I think it was 11. And this was all done on AWS. So the AWS setup, there's an NFS server that hosted all of the data files needed to feed the cracker. All the software was on there, and output was written there to directories named by job ID, so they wouldn't overwrite each other. And so that was an on-demand instance, and then I used a bunch of spot instances for the actual compute. If you're not familiar with AWS, spot instances are a way for Amazon to sell capacity that they otherwise would not sell by letting people bid on it. So if you want to do a bunch of compute and nobody's willing to pay full price for certain type of instance at that particular time, Amazon will let you do it, let you use it for a steep discount. The instance types I use, typically you get an 80 to 90% discount by doing it this way. The caveat is, if anybody else wants to spend more money than you, your instances go down with 2 minutes of warning. So it's good for certain kinds of workloads where you can split the work up and keep track of what you've processed and restart, redo interrupted work. It would not be a great way to run a web server, for example. So this, with a bunch of spot instances, I had to have some way to distribute jobs. So Amazon has something called Simple Queue Service. And what Simple Queue Service does is you set this up, you set parameters like whether you want exactly one delivery, first in, first out, how long, whether you want the messages to be resent to a worker if a worker doesn't confirm that it has finished processing by deleting their job. And they have nice Python libraries for interacting with that. So that's what I did. I wrote a Python script that added jobs to a queue, and then a script that ran jobs from the queue by just executing them directly, which is completely insecure, but it's my job queue. And then one copy of the script run per virtual core. So here's what accessing the SQS API looks like. Credentials removed for obvious reasons. Just a couple lines of code to set it up. Then to read the job queue, I have a get1message function that calls receive messages maximum 1. Really straightforward. And then to actually run the jobs, there's just a pretty simple loop. And all of this is started up using the cloud init functionality that most AWS instances have. And this is, when you start it up, you can say, okay, I want 30 machines, and they should all run this shell script when they start up. So the shell script will have them mount the NFS files, or mount the NFS file system, execute the job runner script, and anything else you want to do, like you can install updates or whatever. And let's look at some example cracking jobs. So the Hashcat utilities are fantastic for all of the pieces that I don't want to implement myself as far as password candidate generation goes. So this first one is using a tool from Hashcat called Mask Processor. And what that does is it just generates passwords based on a mask. This is some specific ASCII characters followed by, it's like, yeah, 4 lowercase letters. So, yeah. So it'll iterate through all of the possible ones. And the reason it's picking out specific characters is because there will be, I had a couple thousand of these running with different first characters. And they all wrote to outputs, which were then merged at the end. Then Combinator 3 is another tool that I was using to do some of the XKCD passwords, had to split this up into a bunch of sublists as a way to divide up the work. But what this tool does is you give it 3 input files. It takes the data from each file and outputs every combination on standard out. So anything that can read from standard in on standard IO can use this as input for cracking. So this is, I don't know how many of those jobs total there were, but this looks like it was job 925. Other shell shenanigans, this is going through the Skull security word lists that I had, picking out the .text files, removing the redundant versions, removing rocku because I did other things with rocku, and then passing it through cat to combine them all together, and stripping out DOS-style new lines because DOS-style new lines are no fun. This used a feature in Brainflare where it will start, in this example, start at the 5th password given and then only process every 16th. Final example is just the hashcat CLI, taking in a combination of rocku, MySpace, and LinkedIn, and running, in this example, the LeetSpeak rule set on it, and passing it in through Brainflare. And the shell script is a really simple thing. It just has common parameters preloaded so that I didn't have to put it in every job. One of the interesting things I learned, my first attempt to distribute data files was to put them in an EBS snapshot, which is, I think stands for Elastic Block Store. Lots of 3-letter acronyms on AWS. So that was incredibly slow. It turns out that the first time you access a block in one of those, it has to fetch it from S3, and it goes somewhere. So this was just unbearably slow. So I went with NFS instead, which still takes a long time because it has to copy. Brainflare usually is loading up about 20 gigs of files to do its run. It has to copy those all over the network, which takes some time. The other thing is the spot instance price can vary a lot between regions, and if you want to do large jobs, you have to call Amazon and say, hey, I know what I'm doing. I will not get myself into millions of dollars in debt by running way too many instances. Please let me run more. So you have to get a limit increase approved, and like if you don't have a limit increase in the right region, that can be problematic. If you've got an AWS account and you're planning to do something like that, you got to do it a couple weeks ahead of time just to make sure there won't be problems.
Okay, so Ryan dealt with getting all of the passwords, processing them, seeing which ones were actually in the Bitcoin blockchain. Then the next thing is to find all the transactions to the passwords that are actually in there. As a first pass, we had an entrepreneurial undergraduate who wrote a program to download the blockchain, gather transaction data for each of these brain wallets. However, we don't get that granular of data when we're doing it on transactions that happened years and years ago. The attackers also drain way too quickly for us to pick up information, because you get about a 10-minute granularity when attackers are working within seconds. So what we did is we use the blockchain.info API. They can give us when the transaction that put money into the wallet occurred, and then the next transaction a couple seconds later when the attacker drained the money out of the wallet. This isn't as defensible as downloading the blockchain, so we also sanity checked it using the first method, and it's same information, different granularity of time. So Ryan took 3.9 trillion candidate passwords and from a bunch of different lists. Now this is a edited version because there's all of those lists that he talked about, but these are the most interesting ones. We can see one that really sticks out is the Reddit one. That was Reddit comments, Reddit usernames. We see that on this far-hand column, it's the money in US dollars, so it's the most. It also has a lot of the really unique ones in the data set. There's some other interesting ones. So LlamaSoft gave us some data that's used just for you guys today. It was 275 wallets. They're all unique in the data set. And it's actually quite a bit of money. It's about $50,000. We were surprised that brute forcing didn't get more. There's only 84 unique and only about $24,000. And then for miscellaneous, that was some old data, that was some combinations of data. Those were all unique because we tossed out anything that wasn't unique. So there is about 2,000 total distinct brain wallets, just over that. There's just under that distinct number of passwords. That's because some passwords were turned into two brain wallets, one compressed, one uncompressed. We also found about 3,000 Bitcoin. Now that sounds like a lot of money, but a lot of this was lost back in the day when Bitcoin wasn't worth that much. So what we did is we converted it to the amount of US dollars that it was worth when it was put in, and that's about $300,000. So it's a good chunk of change. We know that we're necessarily missing things, right? So we only have information on brain wallets where we actually knew the plain text, but it's still a good amount of money. We have some notable passphrases. So the first brain wallet that we found was this string contains 0.25 Bitcoin hiding in plain sight. Some guy posted this in the Bitcoin forums back in 2011. It was the first real time that people started using these brain wallets. And around the time of his post, people in the forums also created other similar wallets. It was the first kind of community around brain wallets, however unfortunate. Now, the second one is the empty string. This is the most common brain wallet, and I don't think anybody actually ever intended to put money there, but a lot of people did, and a lot of people lost a lot of money. This is because of software errors. It was also one of the default passwords on brainwallet.org, which people used. So if you didn't understand what a brain wallet was, and you went to the website, it would automatically prompt you with a private key and a public key that associated with it. And the private key was just the hash of the empty string. We found the most amount of Bitcoin tied to this phrase, Bitcoin is awesome. Now this person put the money in and then he drained it himself. We found 500 Bitcoin. Now the drain that Ryan did, the woodchuck drain, while that one had fewer Bitcoin, so Bitcoin was awesome is 500, Ryan's woodchuck was 250. Ryan's worth a whole lot more because the price of Bitcoin at the time of the drain was not insignificant.
If anybody hasn't seen my previous talks, I put the money back because I emptied it on accident, and then I found the guy and got him to call me, and I explained why this was bad, and he was happy.
So we noticed that we normalized the price of Bitcoin to US dollars, and that's just because the price has fluctuated a lot over the course of the time. And Bitcoin brain wallets were actually somewhat popular in 2011. So the first post in the forum that started off Bitcoin was in July of 2011, and we cut off our data collection in January of 2017. The bars is the number of new brain wallets used every month. And then that is this axis. So in 2017, there was a couple created. We can see that there was a bunch more created in 2013. The gray is the uncompressed brain wallets, and the black is the compressed. Now, what's really weird about this is the most popular type of Bitcoin wallets more recently are compressed wallets. You save money because you pay a transaction fee based on the size of your transaction, and compressed keys are smaller than uncompressed, so you actually save a little money by using compressed. We note that the default standard for most of the Brain Wallet websites is uncompressed, which is why we see this trend. Though we do note that during this time period here, compressed keys weren't available yet in Bitcoin. It is still the early days. Now in the blue line, what we see is the new wallet value in US dollars, and then that axis is over here. And we see at the beginning, while there's some Brain Wallets that were created, they weren't actually worth very much because the price of Bitcoin wasn't actually very high. And we can see it approximately tracks the popularity, though there's a couple of big fish that put in quite a bit of money. So on one hand, here we're looking at the user behavior. We can also take a look at the attacker behavior. So we can look at the time that it takes for an attacker to drain a Brain Wallet. So in black, that shows the overall amount of time to drain. So our time to drain metric is the time from when the user puts the money in the wallet to the time that the attacker drains the money out of the wallet and puts it in his own. We used a cumulative distribution function. So we can read this chart as on the bottom is time in hours, and on here is our cumulative distribution. So in seconds, about half of all of the ever drained Brain Wallets were drained. And then we can see about 80% took about half a day. And almost all of them, 99% of them, were drained within 24 hours. Now, there's some speculation that attackers were colluding together and they were trying to not drain wallets that only had a small amount, because some users were using this to test the security of a Brain Wallet. So some people thought that maybe if you get them to wait a little time, it's not drained, then they'll put a bunch more money in. We can't really see that effect. So in the red and the blue so the red is wallets that had less than a penny in them. Blue is less than a tenth of a penny. While it's actually significantly different than our overall trend, a lot of that is because transaction fees, right? So you're not gonna, if you're trying to drain a penny, during some amounts of time, you would actually have to spend a penny to get that transaction on the network. So it's not actually worth it. And so what these attackers would do is some of them would wait for more things, and then some of them would wait for a mining pool that would just take a transaction with a lower fee. Now we can look at how the attackers changed their behaviors over time. So in the early days of Bitcoin in 2011, 2012, attackers took a longer time to drain those Brain Wallets. There's fewer attackers. So we looked at the number of unique addresses that these Brain Wallets were drained to. So a lot of times the attacker wanted everyone to know that they had the money. So they would have one unique address. It might be a vanity address. And we can see that it goes down to 0. So here in 2014, the median time to drain is seconds. It picks up again. So in 2015, there was a lot more time with just all transactions that spent. And so it took longer for any transaction to get on the network, and Brain Wallet transactions were no different. Now, we also want to know 2 questions about the underlying passwords that were used. So on one hand, we wanted to know if user behavior changed. So did users put more money into Brain Wallets that were better that were more complex, harder to guess. On the other hand, we wanted to know if attackers, because there's just so many of these brain wallets that were with really insecure passwords, were attackers actually going after more complex passwords, or were they just sticking to the easy-to-get ones? And so what we did is we measured the complexity of each of the passwords that we found. We used ZXCVBN, which is a password metric. It's developed by Wheeler at Dropbox. It's one of the canonical measures. We actually tried out a couple other ones, but they gave us about the same results. And we tried to see if more complex passwords affected anything. So we looked at every single thing we could possibly try to throw at this. We used Spearman's rank correlation coefficient. And we couldn't find that it was significantly correlated with anything. So we don't actually see any effect of password strength on anything. This is actually in line with literature. So if you do a bunch of user studies and people have looked at passwords that users use for bank websites compared to throwaway websites, users don't pick stronger passwords when securing more money or when securing money at all compared to anything else. That's the same that we found. We also noticed that attackers don't prefer more complex passwords. They just like more money.
2 quick notes about ZXCVBN. 1, if you don't understand the name, look at the bottom row of a keyboard. 2, it is very much designed for passwords, not passphrases. So,
which is why we have the next slide. So the next slide, we tried to look at the length of the password, and we could see that the 0 to 5 character passwords were drained much quicker. Those are in green than the overall, which is in black. However, we tried to look at longer passwords, which are in blue, aqua, and red, and they're not actually significantly different than the overall trend. So we can see that small number of character words, which are likely to be passwords and not passphrases, are drained quicker. We don't actually notice any difference between passphrases and the overall effect.
Right. So people taking money from weak Bitcoin addresses is not limited to brain wallets. There's a lot of other bad key generation stuff that has happened. One of the most notable was some Android wallet software was not using proper random nonces. And if you create 2 transactions with the same signature nonce in Bitcoin, that is sufficient to derive the private key, which is a problem. The popular brainwallet.org tool had a random button on it, which would just generate a random key for you. But it worked by calling the math.random function from JavaScript. And that was not very random. In Firefox in particular, the random number generator is seeded essentially just by the time of day that the page was loaded. So that's rather easy for an attacker to replicate.
And that was the random function on brainwallet.org. So a lot of users were actually using these things and thinking it was secure.
Yeah, I actually talked to somebody who lost money because of that. Other tools allow users to, they generally are used with random seeds, but the user can select their own if they try. There's a bunch of published example addresses that have published keys with them, and I've seen those cleaned out whenever somebody sends to them for whatever reason. Also, random arbitrary constants are sometimes used as private keys for reasons that I cannot begin to speculate about. I've also seen random data from the blockchain used as private keys, hashes of files. Then Ethereum, there was this site called EtherCamp, and it did a cache of the password, and it didn't tell you that's what it was doing. You'd go to the site and hit generate new address and say, oh, here's a password, and it didn't say how it worked. And I suspect some people got burned by that. And then after I called the guy out on this, he was like, it's not a problem, it's not a problem. And then a bunch of other people, yes, it is. He replaced it with something that still was not secure. I think it does 213 rounds of Kashek because nobody has rainbow tables of that or something. Then there's the Ethereum parity wallet, which has been in the news lately because they had a bug in one of their multi-sig contracts that caused that resulted in a theft of $31 million worth of Ethereum. Not a private key problem, just Ethereum has smart contracts. If they have bugs, they can be real big bugs. And then weird payday script hash stuff. So here's some private keys. They're all empty, but feel free to check. And this is a bunch of weird stuff. So the first one is the SHA-256 of one of the default pictures that comes with Windows 7, chrysanthemum.jpg. How I found that? I fed the contents of my hard drive as raw private keys in. What that hash was doing on my hard drive, I cannot tell you. The next one was a Bitcoin transaction ID. The next one was another, it was on my hard drive, I don't know why. It was just a bunch of, it was just part of pi represented in hex as, the fractional part of pi represented in hex, although it was raw bytes on the disk. Another was a zero padded hash 160 of that address. Found one that was 1234 in ASCII, prepended with a bunch of nulls, which is, of course, the brain wallet an idiot uses on his luggage. The next one was N, which is the order of the curve, minus 105. And about a week or two ago, somebody sent 10 Bitcoin to that, and it disappeared right away, and this person was kind of sad. But he said it was his fault. I messaged the guy on Bitcoin Talk trying to find out what happened there. Another chunks of raw data from Bitcoin transactions, block hashes, other random strings of bytes that were on my hard drive for who knows what reason. The SHA-256 of the Bitcoin paper was used as a private key, and then the last one was just one, and I don't know what to say about that.
We also found some other interesting things. So there's a couple ways of making Bitcoin transactions. We looked at pay-to-script hash also, and we found 139 Bitcoin brain wallets. They're first seen in March 2012, and actually quite a number of them are still undrained. Most of that money is actually all in one of the wallets. There's ethical reasons for us draining it. There's ethical reasons for you not to drain it too. The ones that were drained, though, again, were drained in 24 hours. The median drain time was 9 hours. So they're about like the other ones. They actually have a similar group of attackers. So about out of the 100 ones that were drained, there's about 25 different people who drained it, and 13 of those also drained brain wallets, and at least 8 of them were spam attackers originating from the same group. And one of them was a mining pool. And we'll talk about both of those later.
Yeah. About those ones, the pay-to-script hash ones that aren't drained, I believe all of those were to addresses for which there is no way to satisfy the script to make it spendable. So Yeah. So the Large Bitcoin Collider is a interesting project that somebody started up on the Bitcoin forums, and this is, if you remember SETI at home, if this is that for Bitcoin. It's just sequentially searching all of the keys until the end of time, or whenever somebody decides that they're done burning electricity on this. So they're doing an incremental key search, and they're only searching for keys with a balance, which really disappoints me because it is interesting to see keys even if they don't have a balance. The admin claims that sweeping funds as lost and found is legal in his country, which is somewhere in Europe, and I have no comment on that claim. They have a GPU accelerated client that is able to do sequential search only. It is launched by a scary piece of Perl code that will execute arbitrary code from the server. That was also, there was a debacle about that. Some people tried messing with the script and it started deleting itself after the server sent back a kill command. People weren't happy. They actually did hit some keys with small balances. These were likely original keys, not collisions. None of them had very much in them, and I assume they were tests. There's also this puzzle transaction. I wrote a blog post about it, but basically somebody made a Bitcoin transaction with 256 outputs, each of which had one more random bit in it than the last. So it would be a bunch of 0 bits followed by a 1 bit followed by random bits. And so they're chewing through that, and they've gotten up to 2 to the 52. And like they're not going to find anything from anyone who used a proper random number generator.
So most of the transactions that we've looked at have been of the sort user's money gets drained to an attacker. In the early days, that's what they look like. They might leave a small transaction fee for the mining pools. Later, when the time to drain went down to seconds, one way to have your transaction be the one on the blockchain is to give a larger transaction fee to the miners so that it gets put on the canonical chain. So we're used to seeing that sort of thing. However, we noticed that there was a number of brain wallets that were just drained completely to transaction fees. And that's what this slide and the next one talk about. So we saw there's only 8 different mining pools that did it. They drained quite a lot of brain wallets, though the amount of money was quite low. So they only, in all of these drains, it was like less than $500. So clearly they're not doing it for the money. Well, not clearly, but they're not doing it for the money. But why? So in Bitcoin, what was happening is people were putting like the lowest number of Bitcoin that you can into brain wallets. And they were just flooding what are known as the unconfirmed transaction outputs. So people who want to run Bitcoin nodes, each mining pool has to run at least one Bitcoin node. It eats the disk space. So it's all of the transaction outputs from previous transactions that still have not been spent. Now, one group of people that decided to abuse this was in the Bitcoin block, the network stress test, where a bunch of people advocating for bigger block size caused mass disruption because that's what people do in Bitcoin. And they were set out to create a 30-day backlog of transactions. They achieved it. They put a bunch of money into 15 brain wallets and some other types of easy-to-guess keys. And they put a bunch of Bitcoin in it. And the mining pools then drained it so that It really reduced amount of consumption on the network. Though if we do look at the dates, mining pools did that before the stress test and after. So before we end our talk and ask for questions, we'd like to thank people that also worked with us on Brain Wallets. So this is largely based off their chapter from my dissertation, which was largely based off of a paper that Ryan and I wrote along with Joe Bonneau, who's at the EFF in Stanford. He's a password expert. Cameron Keith, who is our entrepreneurial undergrad, and Tyler Moore, who is my PhD advisor. We'd also like to thank Filippo at Cloudflare, who did an earlier talk with Ryan at Hope, I believe, on Brain Wallets. We'd also like to thank Lamasoft, who gave us data that we used on this version of the talk. And as a conclusion, this is a screenshot of a website run by EtherCamp about why Brain Wallets are the best. And we're just like, no, just no.
One thing I would like to say about that, in this blog post, a challenge Ethereum wallet was posted, which I believe at current value is worth $70,000. And my estimate on the compute cost using AWS spot instances to crack it is about $50,000. So if anybody really thinks this guy wasn't lying, you could do that. Because he said it was available for anybody who could find the password to take. And questions?
Yes.
So I actually have two questions. One is, how did you determine it was a Brain wallet versus a regular wallet? How could you distinguish them on the blockchain?
So the question was, how do we distinguish whether it's a Brain wallet or a normal wallet? What we did is we did that by guessing the password. There's no way of just looking at a wallet and saying what it was, but we only looked at things where we knew the password.
And then the second thing is that there's some questionable services out there. I'd like your opinions on things like the randomsanity.org project from Gavin and Dreesen.
I am not familiar. Oh, that.
So the question was about the randomsanity.org project by Gavin. Ryan, do you want to comment?
I have no comment on that service.
Yeah, I don't either.
Okay, can I talk to you afterwards where it's not on the record?
Sure.
Okay, next question.
So, have you ever come in contact with any of the drainers and spoken to them?
Okay, so the question was, have we spoken with the drainers? Ryan?
Yeah, one of them reached out to me after the paper that Maria and I wrote for FC last year was published, and was kind of bragging about his exploits a bit, and mostly just wanted to get paid for data, and we did not pay him for data.
Yeah, he wanted a lot of money for like the plain text of the empty string.
Like if he wanted a tiny bit of money, maybe I would have paid it out of pocket. I've actually I plan to set up a website eventually to offer bounties for Brain Wallet planes, but I have far too little free time.
Yeah, we also had some money that was just that we were only able to spend on Bitcoin-related research projects. So if it was actually good data and a small amount of money, we could have paid it. But.
Yeah, but he wanted way too much money.
Yeah.
So that's also like there are a lot of people who think that it is totally ethically and legally fine to drain Brain Wallets. I think those people are assholes, but on public forums, people have bragged about this trivially attached to their real name. Like if anybody's familiar with Hacker News, somebody was recently bragging about cleaning Brain Wallets out on Hacker News.
Yeah, and there's also, I've met people in person who have talked about it and talked about their quack legal theories of why it's okay.
Yeah. There was also a guy who was on Reddit for a while who would take them, and then if somebody posted on Reddit, hey, where did my Brain Wallet go? He would give it back. Went by BTC Robinhood. I talked to him a bit.
Yet another instance of people doing ethically questionable things out of the goodness of their hearts.
Yeah.
Next question, yes?
So one other question is, did you where they siphoned the money to? Do you have like a percentage of people that immediately shape-shifted the funds, or what vaults that fund ultimately got to, or like the actual life cycle of the hack?
So he asked if we track the funds after they left the Brain Wallet, the next steps. We tried originally because we thought that maybe there was going to be a bunch of people that owned a bunch of identities that were draining Brain Wallets. What we actually saw is that mostly they drained to one single wallet, and we could see some amount of people mixing their Bitcoin after it left, either using a mixing service or by gambling, using Satoshi Dice at all. But we didn't so we tried to do it, but there wasn't actually that much there. Are there additional questions?
I guess not.
Okay, great. Thanks for coming.